This video is going to cover Cox proportional hazard models. I did another video just kind of laying the groundwork for survival analysis, and that one might be worth taking a look at first if you're not familiar with that, because this one's just going to focus on the modeling process itself. So hazard, sometimes called instantaneous force of morbidity or mortality, is the probability of having an event between a specified time t and some other time. So probability of having an event between this time interval, given that the event hasn't happened yet. And yeah, just to kind of, that's not as important as the actual structure of the model. So it's called Cox proportional hazard function because this hazard, the baseline hazard here in the non-exposed group, and the increase in hazard as a result of exposure is a constant proportion that is the same across all values of time. So although hazard changes over time for various reasons, the relative increase in hazard due to exposure is constant over time. And this lets us find one measure of effect for what effect this exposure is having that describes the relationship across the entire follow-up period. So this is just a mini version of the Cox model. We have the observed hazard here. That's a function of this baseline hazard multiplied by the effect of the exposure. And it's on a multiplicative scale, so we have to exponentiate beta to get that actual effect. Something to note, the intercept isn't its own term like we're used to seeing. It's grouped in here, multiplied by the effect of the exposure. And that's not typical, but that is one of the idiosyncrasies of the Cox model. So we're able to divide by h naught to bring the h naught back over here. And now we see that the hazard ratio, the ratio of the baseline hazard and the increase due to the exposure, is equal to the exponentiated coefficient on our treatment here. So that's equal to the hazard ratio. So something else to notice is it's not a function of time, although t shows up here in both cases, doesn't show up again. So that's due to the fact that this ratio is meant to be constant over time. So just illustrating a bit more why beta 1 is the hazard ratio. If our treatment effect, or our treatment here is a categorical variable, it's when it's present, that's equal to 1, and it's still h naught and beta 1. But when x is absent, a 0 would go in there, and that would cancel this term, leaving just h naught t. So if we have a ratio of the hazard given the exposure is present over the hazard given the exposure is absent, we have h naught times exponentiated beta 1 just over h naught, and that can cancel, just leaving exponentiated beta, which is a value representing the relative increase in hazard as a result of being exposed compared to the baseline hazard in the non-exposed. Yeah, that's what I just said. And yeah, people don't often report it as a hazard ratio. A lot of people wouldn't know what that means, so it's easier to just report it as a relative risk. And how beta is estimated is an iterative process with the software will do. We wouldn't do it, where this is the likelihood of a value beta. We're trying to maximize that likelihood given what we know about each subject at each time period, basically. And we're able to come up with a value of beta that makes the most sense given the data that we have, or a computer will find that. It assumes no ties, but there's methods available to deal with ties that you usually don't even need to specify to the software just because it's so commonplace. So this is an example where we're looking at whether a new cardiac surgery will result in people surviving longer than the standard treatment, given that we've controlled for sex and age. So this is the structure of our data set. We have 4 observations here. We have their treatment status, their sex, age, the time they were followed, and whether they were censored or not. So observation 1 was followed for 6 years, and they stopped being followed because they were censored, as opposed to individual 3 here, who was followed for 9 years, and they did their follow-up time stopped not because they were censored, and the only other reason it could have happened is because they had the event. So that's basically how we tell the software whether someone's time stopped because of their event or because of loss to follow-up. And just kind of coding, just putting like wherever was standard treatment 0, new as 1, female referent, and censored as 1. So yeah, and that's how our data would look. And this would be our model where we have the observed hazard is a function of this baseline hazard, the effective treatment, the effective sex, and the effective age that are all increasing or decreasing our baseline hazard. And let's just say we got this output. For sex, we got a coefficient of 1.22, significant. Treatment, -1, significant. Age, 0.15, significant. And because it's a multiplicative scale, we need to exponentiate this coefficient to get a measure of effect. So when exponentiated, the hazard ratio for sex is 3.38. And because we had females as the referent, that means that males are at a 3.38 times greater risk of coronary heart disease than females when controlling for the other 2 factors, treatment and age. Exponentiating treatment, we have 0.36, and interpretations when it's below 1 can be tricky, so the best thing to do is to express it as a percent change. So here we're able to figure out that those receiving treatment have a 64% lower risk of mortality than those receiving the standard treatment, controlling for sex and age. And just to give an example with a continuous variable, we have age here exponentiated, comes out to 1.16, so mortality risk increases by 16% for each 1 unit increase in age, which I believe it's years here, so for each 1 year increase in age. The proportional hazard assumption is key to this modeling process, and there's some situations where it might not be true, and depending on what's contributing to the violation of this proportional hazard assumption, there's some ways you can stratify the analysis or stratify the estimation of beta in order to account for this. And basically, let's just say it's not constant among males and females, then we're able to do 2 separate Cox models, one for males and one for females. And this beta 1 estimate through the maximum likelihood process takes into account, now it's not just looking for a beta value that makes the most sense given this data on males. It's trying to find one value that best explains the differences, both accounting for the data on males and females, which is not typical when we use the word stratified. Like typically when we do stratified analysis, we get a different measure of effect for the 2 strata or the 3, however many strata. But this is another idiosyncrasy of Cox regression, where we can get one beta that describes both strata, even though we estimated beta through a stratified process. Also, there's a possibility that this ratio of hazard from exposure and baseline hazard might not be constant across time. It might be proportional for a bit, and then it might change. This ratio might go from being like the exposure doubles the risk relative to that to all of a sudden it's 4 times. And we can do that by trying to figure out where this change occurs and stratifying by follow-up time or calendar time, whatever we're attributing it to. And ideally, the proportional hazard assumption will be met within those strata.